electrical vehicles are considered as most environmental friendly for modern transportation system. The demand for electric vehicles are becoming more mainstream day by day due to increase in battery capacity and decrease in battery cost. Just like internal combustion engine based automobiles need for more gas, petrol or diesel stations, in the similar way, the electrical vehicles will demand more charging stations. If you look at the traditional electrical vehicle charging structure, it will be like this. Between grid or source to load, power electronic devices like inverter and choppers will play a crucial role, and it is responsible for converting as well as controlling the electrical power in charging systems. Here we use inverter to convert the source AC to DC because our electrical vehicles need only DC. Then we use the chopper like DC-DC converter. Here we are using the buck converter to convert high voltage to low voltage DC because our electrical vehicles need only low voltage DC, but our grid have higher voltages. So to convert the higher voltage into lower voltages, we are using the buck converter, that is nothing but DC-DC converter here. And to deliver the electric current for charging or discharging of electrical vehicle batteries, DC-DC converters along with the control system, will be used. Because in our DC-DC converter, we are using the power electronic switches like IGBT or MOSFETs. To turn on and to turn off those switches, we are using the pulse width modulation combination of our control part, and the switching operation produces non-linearity in the system. The stability of output voltage and overall improvement in the system performance can be achieved by control methodologies. Due to simplicity in design and ease of implementation, conventional control like PID control system will be used to control the DC-DC converters. With predetermined and tuned constants, conventional PID controllers are based on mathematical models. Basically, the stability of these PID controllers will be based on constant values like Kp, Ki, Kd. These are nothing but the proportional gain, integral gain and derivative gain. But the major problem with the conventional control approach is they do not work well with the non-linear systems. Their performance can be vary a lot, so it is not good for non-linear systems. That's why in recent years, the design of power electronic converters with optimal control based approach has become highly desirable and finds in many applications. There are so many optimal control strategies like artificial intelligence, fuzzy logic systems, artificial neural networks, and genetic algorithms, etc. These optimal control strategies are far better than the conventional PID controllers because traditional PID controllers struggles with complex dynamics or severe disturbances. Meanwhile, these optimal control strategies have robust and high performance solutions. So that's why in our research we are designing Adaptive Neuro-Fuzzy Interface System optimal control strategy based interleaved DC-DC converter for electrical vehicle charging applications. Here we have so many optimal control strategies, but why we are using only Adaptive Neuro-Fuzzy Interface System here? Because it is hybrid converter. That means it is a combination of two neural network plus fuzzy logic system. So that we have the advantage of combining the learning and adaptive capabilities of neural network with the rule-based knowledge representation of fuzzy logic system. And this ANFIS optimal control strategy has several more advantages. Those are, it can handle non-linear systems well and no need for a precise mathematical models. And also it has a superior dynamic performance, including reduced peak overshoot, shorter settling time and lower steady state error. That's why we are using the Adaptive Neuro-Fuzzy Interface System in our control strategy. That is the first part of our title. Okay. Now coming to second one, here why we are using the interleaved DC-DC converter. We have so many existing converters are there, right? Like traditional buck converter is there and then so many. But why we are using this interleaved DC-DC converter only here for our electrical vehicle charging application? Because it has so many advantages. Actually, if you see the interleaved converter design, it uses multiple parallel switching converters. That means it connected to two or more identical converter modules. For example, if you see our proposed model here Here we are connecting two identical buck converters. This is one and this is second one in parallel in nature, so that we combine their power significantly, reducing input and output ripple and also lowering stress on components and improving the efficiency. This technique will increase power density, enhances transient response and lowers the electromagnetic interference compared to the traditional single converters. And also this converter is ideal for especially high power applications like renewable energy sources and electrical vehicles. That's why in our title for our electrical vehicle charging applications we are using this interleaved buck converter. This is our proposed circuit diagram. Here we are using the two-phase interleaved synchronous buck converter. That is nothing but this. Basically, it is a parallel set of synchronous buck converter. Each set has its own components like inductor and power electronic switches. Such components are collectively called as a phase. The phases are configured in parallel to each other and shared input and output capacitors. That's why it is called as a two-phase interleaved synchronous buck converter. As we discussed earlier, here we are using the Adaptive Fuzzy Interface System to control our circuit. So here at the end of output we will get the load voltage and load currents, right? So it will sense these two, and here we are controlling the voltage loop separately and current loop separately with two Adaptive Fuzzy Interface System controllers. To achieve better controlled output for given input and loading conditions, we are using the separate control loops to control the system. And this output of control will give into this comparator. This comparator will compare this reference with the carrier signal and generate the pulses by using pulse width modulation to give the pulses to our power electronic device switches. Here each phase is spaced between interval of 180 degrees phase shift. It means the two phases are interleaved in nature. This converter switches will be 180 degrees in phase with the second phase converter. That's why these are interleaved in nature. And if you see the power flow, here we are taking DC voltage as our source. Okay, because in grid we are having AC. By using inverter we are converting the AC into DC, and the DC will be given here. Okay, here our main title is designing the interleaved DC-DC converter only. That's why here we are taking our source is DC source and give it to the one input capacitor, and by using our interleaved buck converter we are reducing that voltage to the electrical vehicle battery needed voltage or load needed voltage by using this output capacitor. Then our output voltage and currents will be controlled by using our ANFIS controller. Then the pulse width modulation give pulses to our power electronic devices. Then the switches will be on and off according to it. Okay. Now if you look at the schematic diagram of our control, as we discussed earlier, our controller is combination of fuzzy logic and adaptive neural network. Here, this is the input. Here we are taking the input crisp value. Because we are using the fuzzy logic system, right? So fuzzy logic system need fuzzy values only, not crisp values. To converting the crisp value into fuzzy value, we are using the fuzzification here. So this fuzzification will convert our input crisp signal into fuzzy value, fuzzy set. That fuzzy set decision making will depending on our neural network. That is this block. By using knowledge base training data, it will train the network. Okay, it will train the network and generate the rules for our fuzzy logic. By using that rules, we will make the decision and again we will defuzify it, because our system need only crisp values. Okay, for only controlling, we are converting this crisp value into fuzzy value. After converting, we need to defuzify it. Means we need to convert again this fuzzy value into crisp values. Now this crisp value will be given to our comparator. By using pulse width modulation, we will generate the pulses. This is our overall control block. This is how the combination of adaptive neural network and fuzzy logic system will work. Okay, now we will design this entire network in MATLAB simulation with conventional control like PID controllers and also with optimal control strategy like ANFIS, and look at our waveforms, how it will be performed. Okay. This is our conventional MATLAB model. Here we are using the PI controller for our circuit. So here you can able to see this is our DC source we are taking here. This is control voltage source, and here we are taking the DC. And the source voltage is given by this lookup table data, and then we are taking the input capacitor, and here this is voltage measurement we are taking to measure the input voltage. Okay, we are connecting parallel to our source, and then we are using the first phase converter. It is a interleaved synchronous converter, right? So here this is the first set, nothing but the first phase, and also this is the second phase. These two are connecting parallel to each other. That's why it is called as interleaved synchronous buck converter. And then we are using the output capacitor to give to the load. This is our load, and here we are using the load voltage measurement to measure the output voltage. and here we are using the output current measurement to measure the output current. Okay, and below we are taking the output voltage and output current loops to control the voltage and current separately by using traditional PI controllers. And by using this comparator, we are comparing this output reference with the carrier wave to generate the pulses for our power alternating switches. Here you can able to see this switch S1 and this switch S2 both in same leg. If you turn on these two at a time, it will be open circuit. If you turn off these two at a time, it will be short circuit. That's why in below control part, we are using the S1 and S2 with the help of NOT gate. That means whenever S1 is on, it must be off. Whenever S2 is on, S1 must be off. Okay. Similarly, for the second leg also, S3 and S4 also, we are using the NOT gate here. Now you can able to see output responses in this below scopes. Now just run our simulation to see the output. Now click on the scopes. You can able to see this is our output. So you can able to see it is taking more settling time to settle in steady state, and also it has overshoots whenever the load changes. Now see the same circuit with the help of our optimal control strategy. This is our proposed model. Here we are using the same circuit, but here only changes our control strategy. Here we are using the Adaptive Neuro-Fuzzy Interface System. Now just run this simulation and see the waveform. Before running the simulation, you need to import and export the fuzzy logic rules, because we are using the Adaptive Neuro-Fuzzy Interface System, right? We need to import and export our fuzzy rules. Okay. For that, go to command window and here type fuzzy, FUZZY, and click on enter. Now import the data. Import from file and import our data. Now export to workspace. Click on OK. That's it. Importing and exporting our fuzzy file is over. Now you can directly run the simulation. Now it is ready. Now click on the output response. Now you can see here, this is our proposed waveforms. Here you can able to see it is taking very less time to settle. Okay, it is having very less time to get the steady state, and also it is very less overshoots. Okay, when compared to traditional PI controllers. Now you can compare these two waveforms. Here it is taking too much time to settle. Here it is settled in very quick manner, and also when the load changes, it is having more overshoots. So here it have only less overshoot when the load is changes. That is what we need to observe here. Okay. Finally, we can able to conclude when compared to traditional PID controllers, our optimal control strategy like Adaptive Neuro-Fuzzy Interface System far better than the PID controllers. Okay. That's it for the project. If you want for this extension, you can use with different control strategies like genetic algorithm or model predictive model. You can compare those all models with the existing PID controllers to observe the response. Okay. If you want this project, then contact me. I will help you in deeper explanation, and also I will give complete assistance. Thank you.